Okay, so now I'm going to switch to a somewhat different topic. So it's not directly the topic of forward proofs or structured proofs, but it's also closely related. It's very fundamental in Lean. It's the notion of dependent types. So you might remember at the beginning of the course, I talked about dependent type theory. I said this is the logic of Lean, but at first we only covered simple type theory. Well, now I'd like to explain what a dependent type is, and we're going to revisit the typing rules that we saw in the first lecture so that they can account also for dependent types. And I must warn you, this is one of the toughest segments of the whole program, of the whole course. At the same time, once you understand it, once you understand dependent types, then it feels very natural, very easy, even something that you, in some sense, might feel you knew about all along, just not under that name or with that syntax. So I would say this is also a moment where you shouldn't panic if you don't understand everything first time around. And if my explanations seem a bit incoherent, then just wait one day, read the Hitchhiker's Guide, or just do some exercises, and then the concept will sink in over time, if nothing else. All right. So I'll start with a. This is mostly textual here. This is conceptual, right? This is basically a short version of the text in Hitchhiker's Guide. So to illustrate what a dependent type is, we'll consider a function called pick, which picks a number. It takes a number n as argument, and it picks or returns a number between 0 and n, right? So if I say pick 3, then it would return 0, 1, 2, 3. I mean, it's not really a function, or well, if it's random, then it's not really a function, but would be more like a randomized procedure or something. Or it could be a function. You just, would return a number between 0 and 3, always the same one. We just, maybe don't know which one. Okay. So what we'd like to give the signature of pick. We'd like to say, well, pick takes an integer and returns an integer. And normally, or a natural number, normally we would simply write something like this, right? N to n, right? We'd say takes a natural number, returns a natural number. But that is not very precise. We'd like to say that if it takes, number 2, then it returns 0 to 2. If it takes 5, then it returns number from 0 to 5. And this is what we'd like to write instead. Right, that it takes a number n of type natural, and it returns something in the interval 0 to n. Right, this is a Lean syntax that I'm using here. It's a set of all integers I such that. So this is such that I is less than or equal n. Right. So informally, we would have written this maybe. Right. Sorry, no, this. There. So it goes from n, right? But we're going to use the other syntax because it's actually quite readable and it's the official Lean syntax. And we're going to see it again later in the course, so we might just as well learn it now. And another way to look at it is to think of this as a parameter, right? So you can think of, well, pick of n has this type, right? Which is the right-hand side here, right? So for all n, pick of n has this type. Something is wrong with this type. Sorry, I will just correct it. This is not nx, this is n. So I'll fix it also in the repository. Sorry about that. Strange typo. Taking notes. Okay. So what we have here is an interesting dependency. We have a dependency between a term, the term n, and a type, this whole type here, right? And this is usually what we mean by dependent type, right? Because to have terms depending on terms, well, that's simply not dependent types. To have types depending on types, we have that all the time. For example, list is a type that depends on a type, right? So you give it a natural, you give it not, and it gives you list of not, right? So this kind of dependency, I mean, technically is also a dependent type, but usually we'll keep the phrase dependent type for dependency from term to type. All right, and here are some more examples. We can have a term that depends on a type. That would be, that's quite normal. Like here, this term here is polymorphic, a type variable at the front. So that's the other direction, but that's quite harmless. And you also have, right, this direction we also had, and we also have terms depend on terms, right? So in short, we have 4 cases, right? The term depending on term, this is the simply typed lambda calculus. Then you have type depending on the term, that's what we will call dependent type and most people call dependent type. And you have the term depending on the type, that's a polymorphic term. Which we will not encourage, well, we will meet some of them, of course. Yes, some polymorphic functions are examples of that, right? So operations on data structures like lists, which are polymorphic, will be polymorphic terms. And then type depending on the term, type is basically a type constructor like list or such expressions, right? And now we see the revised type rules. So we have the same rules for const and for var as before, but we now have a modification for app and lam. So I've added little apostrophes to distinguish. And what's the difference is that suddenly the types, what used to be just tau is now tau bracket of something. And the same thing here, tau bracket of something. So previously this had type tau and this had type tau. And here, well, if you don't use the X, we might just as well omit it. So this was the old rule. And now what we've done is, whoops, I went too far there. What we've done is we've given a name to the argument here so that we can refer to it in the type, right? It was like pick n, right? We need the n to specify the type. Here is the X. We need it in here. So this is tau, you know, of use. It's some term tau, some type tau that contains some subterm u, and here this is the same one but with X in place of it, right? So what's happening here really? Well, here when we apply a function t, which says for any x you end up with tau of x, and we apply it to u, then obviously we're going to end up with tau of u as the type, right? Because this maps x to tau of x, and here we pass u for x. And then the lambda constructor is the same story. So when you build a lambda, the type here, you know, which is the type of your body, may depend on x. You're allowed, not only the t may depend on x, but also the type tau of t may depend on x. And that gets propagated here as well. You see the x here and the x there. The x doesn't change, it's the same x here. This is all just to say you're allowed to refer to x in the type of t, if you want. And again, if you just remove this and remove that, and you say tau doesn't contain x, which by default it shouldn't, then you know, by the usual conventions of mathematics, and here, of course, you don't need this either, right? Then you end up with the old rule. Also remove the prime. Okay, so I'll just undo all of that. And here is an instance of, well, two instances of these rules. So we see with pick, right? So we want to pick, we want to type, you know, pick 5, we want to say it's, you know, the sets of all y's below 5. The name here doesn't matter, all right? And app tells us, okay, we need to type pick and we need to type 5. So that's why we have two premises. And the first premise says, well, you have to have some argument and we're going to name it x. And, you know, that has to correspond to the argument so that when you pass the 5 here, it's going to work. Okay, now I'm thinking too much, actually. I shouldn't be thinking. I should just look at the rule here, right? So I just see, okay, pick is T, 5 is U, C is empty, you know, sigma is N, tau of X is this expression with an X in it, and tau of U is this expression with a 5 in it, because U is 5, right? And the same thing for lam. So this is a whole lam derivation. It has two lambdas in it. So it has a lam here, lam there. For the second one, you can choose between the two. So this one you can look at home, but these are just two instantiations again of the lam rule. There's nothing magical happening here. And this is a dependent type. It's in some sense as simple as that. It's you get an argument, and normally no matter what the argument is, the result type is the same. But here with the dependent type, you want to have the flexibility of changing your result type based on it. Now, two very important remarks. So first, I've used this syntax here above, which is you know, very intuitive, I think, because it nicely generalizes the standard syntax, you know, when there are no dependent types. But this is not supported by Lean, right? I think Agda might support something like this, but not Lean. So in Lean, the syntax is will actually look quite strange to most of you. It's with a for all. So you write for all x colon sigma comma tau, and that specifies a dependent type, right? And if tau doesn't contain x, then you can also just write the arrow, right? And you see the two syntaxes are quite different. You know, one is an arrow, one has a for all with a comma. So it's actually, that's the hardest part, I would say, about dependent types. It's just the syntax. It's just very confusing. But unfortunately, that's the most widespread syntax for this, and it has some advantages. So this is the one we'll have to use. But when you see something like this, you can think of it as being, this is just a function. It's just a function, but we need to name the argument so that we can use it here quite explicitly. It's like this. Right. So this is the first remark, that we have this for all syntax. And the second important remark is we have a bunch of aliases. So first of all, the standard arrow is simply syntactic sugar for a for all, right? So when in the first two lectures I was saying, oh, we have, you know, we have either for all or an arrow. Well, actually I could have said we have a for all, and that would have been sufficient because arrow is a special case of for all. So you just need to, you know, we really just need for all to do everything that we've been doing also with arrow. And second thing is there's a symbol called uppercase pi, and it's a perfect synonym for all in Lean. You can use it, you know, for dependent types, but also for, you know, for universal quantification. But the tendency among the Lean users is to go towards for all, and Lean 4 will only support for all and will not support pi. These are aliases, and alias is always confusing. So, well, almost always. So I recommend you just use for all for everything. So we might see some pi's sometimes in Lean's output because we're using Lean 3, not Lean 4, which doesn't exist yet. But we're not going to use it actively.